Hello friends, today we start another lecture of chemical equilibrium. In first lecture we saw what is the meaning of chemical equilibrium, then we have to discuss the laws of chemical equilibrium, types of chemical equilibrium, and in last we discuss the perfect gas equilibrium. In perfect gas equilibria, we consider the concentrations of reactant and product in the form of mole per liter, or sometimes we express in a partial pressure form. So basically we can already know the equilibrium constant is equal to, this is a power of concentrations of product upon power of concentrations of reactant. So for that we consider here simple reaction is, there is a synthesis of NH3 according to Haber process. So in Haber process use N2 and H2 gas together and they form the NH3. So reaction is balanced here. For N2 we need the 3 H2 molecules which are converted into twice NH3. So according to law of chemical equilibrium we consider Kc, means here C is the meaning of concentration, that means the reactants and products which are expressed in the form of concentration, that means mole per liter. Okay, so Kc is equal to, there is a product, so NH concentration of NH3, and what is the power? Power is 2. This is already told you, the power of concentration is equal to number of molecules present in a chemical equation. So in chemical equation there are two NH3 molecules, means power is equal to their number of molecules. So NH3 means concentration of NH3 with power 2 upon, there is a reactant side, there is a N2, there is no power, so single N2 is there. H2 has 3 molecules, again we consider power 3. So this is the equilibrium constant according to law of chemical equilibrium. But what is the point? Equilibrium constant in a gaseous phase means, what is the equilibrium constant if the reactants and product in a gaseous state, means reaction proceed in a gaseous state, or sometime reaction from the gaseous molecules, means some gaseous molecules are used, they converts into gaseous product, or sometime solid reactants are used, they converts into gaseous product. So if we think that if concentrations are expressed in the term partial pressure, that means Kp is equal to, so P means it is a equilibrium constant in expressed in the form of partial pressure. So Kc is replaced by Kp because here concentration is expressed, here partial pressure is expressed, is equal to, again same equation is here, but what is the difference? Here we use P before the concentration of the species, before the name of the species, that means PNH3, PN2 and PH2 are the partial pressures of the reactant and products. So PNH3, again the power is same, there are two molecules in equation. PN2 because same, there is only one power is there. PH2 there is a 3 powers in the equation. So this is the equilibrium constant in a gaseous phase, if reaction or some reactant and product in a gaseous state. Using this thing we can going to write the equilibrium constants for the different reactions. So 3 reactions are given to you. Write the equilibrium constant for the following reactions. First reaction is KClO3, which is converts into KCl plus 3 by 2 O2, right? So here KClO3 present in solid state, KCl is again solid, but and here O2 is the gas. So only the equilibrium constant, if we consider the Kp, only related to the species which are in a gaseous state. So first of all we write the equilibrium constant according to law of chemical equilibrium. So Kp is equal to concentration of KCl into concentration of O2. So here we use PO2 because of there is a oxygen present in a gaseous state, and if there is a gas has a partial pressure, that means PO2, and their power is 3 by 2 because in chemical equation the 3 by 2 molecules are given. Upon there is a product reactant, so here is a KClO3, but KCl and KClO3 are present in a solid state, and Kp is only related to that species which are in a gaseous state. So here only O2 is in a gaseous state, so Kp is directly equal to PO2 3 by 2. So we neglect this one. So Kp is directly related. Kp is equal to the concentration of O2. There is a 3 by 2 is the power of concentration. Second is calcium carbide on oxidation gives calcium carbonate plus carbon dioxide gas. So again we use same, write the equation first. So here we write the product of reactants, product of power of product side. So calcium carbonate, there is a power is 2, CO2 power is 2, concentration power is 2, but here we express in the form of partial pressure because it is in a gaseous state. Upon calcium carbide O2, the power is 5, O2 again expressed in P, so PO2, that means there is a partial pressure because O2 in a gaseous state. That means these are in a solid state, we again there is a neglected. So only what remain, Kp is equal to concentration of CO2 upon concentration of O2. Okay, so this is the equilibrium constant. For last, again same, H2 plus I2 gives twice Hi, that means all in a gaseous state. So here PHI means product side, their power is 2 because 2 molecules in a chemical equation upon H2, concentration of H2 into concentration of I2. So there is no power because they are present in single form, single molecule. So this is all about, you can use this equation this way, you write the equilibrium constant for the any reaction. Okay, we're going to discuss another problem. Okay, so this is the problem number 2nd. The following results were collected for the two experiments involving the reaction at 600 degrees Celsius between the gaseous sulfur dioxide and oxygen to form the gaseous sulfur trioxide. So it is a simple reaction is given, SO2 plus O2 gives SO3. So to balance this reaction we need here twice CO2, O2 plus gives twice SO3. Okay, this is the balance in the reaction. So when this reaction is carried out, so there is a data is given. In experiment number first, the initial concentrations are given, and what is the concentration at equilibrium. Basically, we consider the concentration at equilibrium. So it is experiment number 1, and in experiment number 2 there is the initial concentrations are given and the concentrations at equilibrium also given. We use this data and to find out the value of equilibrium constant. So here we are going to discuss two reactions, K1 and K2. In both experiments, in both conditions, is it the values are same or different? So there is we can find out the is it error or not. So simple, we consider this reaction. For this reaction, K is equal to concentration of SO3 power of 2 upon concentration of SO2, there is a power is 2 into concentration of O2. Okay, K is equal to, we simple consider K, not a Kp because not a pressure condition is given to you. So using this equation and using this way we can calculate the K in the both the experiments in both condition. So for K1, for reaction 1, K1 is equal to, so here we use same equation because same reaction is there, we just change the value. So for experiment number 1, what is the concentration of given 3.5? So here 3.5 upon, what is the concentration of SO2? Here is a 2, so 2 in the square is given. What is the concentration of O2? It is a 1.24 into 1.25. And the answer is, it is the 4.36. 4.36. For reaction second, what is the concentration of SO3? There is a 0.26, okay. 0.26 to, what is the concentration of SO2? 0.59. What is the concentration of O2? 0.045. So again we find the equation and we find the answers, and the answer is 4.32. 4.32. That means in both cases the equilibrium constant has the different value. There means there is an error in the equilibrium constant. So we can conclude we found the error in equilibrium constant. So first of all, we balance the equation, we write the equilibrium constant for given equation, then reaction is same in both experiments, just values are given. So we just put the values and we get the answers, and the answers are different. That means there is an error in the equilibrium constant. So it is all about the second problem. We're going to discuss third one. Okay, there is a one more problem given to you. Calculate equilibrium constant for the reaction. It is the H2 plus CO2 gives twice H2O plus carbon monoxide CO at 1395 Kelvin. If equilibrium constant at 1395 Kelvin for the following reactions. So the two reactions are given to you. Using these two reactions, we can calculate the equilibrium constant for the given reaction. So we already have the two reactions are given. There two equilibrium constants are given, K1 and K2. Using K1 and K2, we can find out the equilibrium constant for the first reaction. First of all, we write both the reactions. So for first reaction, it is a K1 is equal to, so we write this one. So here concentration of H2 upon into concentration of O2 upon concentration of H2 is the square. I check it first, the reactions are both same. Sorry, the first reaction here is the H2O, not so H2O. So here is the H2O. Okay. For second reaction, there is a K2 is equal to, and again there is a twice CO2 and plus twice CO2 plus O2. Sorry, here is a CO, sorry, because reaction is not balanced. Okay, CO. So K2 is equal to concentration of CO power is 2 into concentration of O2 upon concentration of CO2. It is a power 2. We already get that equilibrium constant values, equilibrium equation for the both the reaction, because we already have their values here, 2.1 and 1.4. Similarly, we force the first reaction which is given for reaction given, sorry, for given reaction, so K is equal to, there is a H2 gas plus CO2 is given. So here H2O concentration of CO upon concentration of H2 upon concentration of CO2. So we write the three equations for both the reactions. First reaction, second reaction, K1, K2, and the K is right for the given reaction. So here we consider the ratio of K1 and K2. So here we consider K2 upon K1. If we consider K2 upon K1, we consider this equation. So for K2 the equation is given, this one. So CO upon O2 upon CO2, and for K1 the equation is given, but it is the proportional, that's why we change the power denominators. Here is the H2O power is 2 upon concentration of H2 and concentration of O2. So this is the K2 upon K1. Okay, we consider both these. So we cancel it, the common terms here. So we cancel this one. So what we remain here is equal to CO, then H2O upon CO2, then H2, because this is the product CO plus H2O, CO plus H2O is the product, CO2 plus H2, CO2 plus H2 in a reactant. So this part, it is a K2 upon K1 is equal to, so we consider this K2 upon K1 is equal to this one. That means it is the K1 and K2, so K2 upon K1 is equal to K square, because this is the multiplication on product of K1 and K2, that means it considered as a K square, because two equilibrium constants we consider K square. So K is equal to, K is equal to, this is the, this side goes in the form of under root K2 upon K1. K is equal to under root K2 upon K1, and we already have the values of K1 and K2, so we have this value. So K is equal to under root, what is the value of K2? 1.4 into 10 raised to minus 12 upon 2.1 into 10 raised to minus 13. So answer is K is equal to, and the answer is 0. The answer is 2.58. So K is equal to 2.58. So using this way we can calculate, because the reaction which is given is the product of this one from it is coming from these two equations. So first of all we write the equilibrium constant equations for these two reactions. They are, we consider their ratio K2 upon K1. Okay, so K2 upon K2. So we neglect the common terms. So remaining equation is balanced for this one. If you see here, H2O, CO at the product, H2 and CO is at the reactant, just power of concentration is changed, because here the two reactions are given, their number of molecules are equal to power of concentration. So this is all about the third problem. We're going to discuss next one here, last one.